So let's start. So in this lecture series, I'll basically cover first the Hamiltonian formulation, and after the Hamiltonian formulation, I will do some example of Hamiltonian formulation. Then I will cover the thing that if you choose to define generalized coordinate, will it change the Hamiltonian or not? Okay, when the Hamiltonian will be the total energy, when the total energy is conserved, and after that I'll derive the Hamiltonian from the variational principle, how you can derive it, and from here you can move to the canonical transformation. There is a Lewis theorem, and when the phase space volume will be conserved, when they're not conserved, after that we will go for the generating function and Poisson bracket and each and everything. So I'm starting from the first, the Hamiltonian formulation. Okay, so first I have to introduce some idea of the Lagrangian formulation also, because we are going from the Lagrangian to the Hamiltonian. Okay, so in the Lagrangian formulation we have L. Okay, what is L? L is equal to T minus V or T minus U. U is generalized potential and V is potential. In general, V that can be a function of the position, but when there is a system when the potential can have some velocity dependency, then we have to consider the U, the generalized potential. That's the first thing. And what is it? L? L is nothing but a function of the q dot and time t. You know this, right? So, and what is your the equation of the motion? This is a ddt of del L by del Qi dot minus del L by del Qi equals to 0, or I can be 1 to n, or n is the total number of the generalized coordinate or total number of the invariant degrees of freedom. Okay. So if you have a system where there is a n number of generalized coordinate, okay, then you have this n number of equation. This is a second order differential equation. Okay, if this is a second order differential equation among, and there is total n number of differential equation, second order differential equations, and then we need 2n number of the boundary value to solve this problem. Okay, after knowing some 2n number of the constants or 2n number of boundary values, we can derive what is your q at a time t. Okay, there's a solution of this problem. What we want to do, we want to write down the equation of motion not in the second order form, we want to write down the equation of motion in the first order form. So if I have to write down the equation of motion in the first order form, then we have to consider total 2n equations. When there is a second order equation, there is total n number of equations. Second order differential equation, there is total n number of equations. If you want to consider first order differential equation, then you have to consider 2n number of equations, because 2n number of first order differential equation can have 2n number of boundary values, and boundary values is coming from the system, so these boundary values should have to be conserved. So when you are talking about first order differential equation, you have to consider 2n number of the differential equation. In between 2n number of differential equation, n equation will be of q, n first order differential equation of the q, and another n differential equation will be some another quantity of some another, would be the first order differential equation of some another quantity is a p. Now what is p? That's another thing. P is known as the generalized momentum, okay, or canonical momentum conjugate to the q, and p has a relationship that p is nothing but del L by del qi dot, I mean pi equals to del L by del qi dot. Okay, so we are going to a system where there is n number of the differential equation of the q, n number of differential of the p. That means there are total uh, there are total 2n number of the coordinates. When we are talking about the Lagrangian formulation, there is a q number of there is a q, there is a q1 to the qn, and n number of the coordinates, and they are forming the configuration space. That are forming the configuration space. And we are going to another coordinate system. There is a q, there is a q1 to the qn, and for each and every q1, there is some conjugate moment also p1 to the pn. That means we have n number of q coordinate, n number of the p coordinate. That means we have 2n number of total coordinates, and this space is known as the phase space. So previous one is the configuration space, and this one is the phase space. Okay, and this one is the phase space. So now look into this. We are going from q dot t. This is the Lagrangian, which is defined in the configuration space, and we are defining some quantity in this phase space, which is nothing but h, which is a function of q, p, and t. Okay, so we are going from Lagrangian to the Hamiltonian, where basically in the functional form we are changing q dot to the p. Okay, in the functional form. So we are going from the configuration space to phase space, and in the functional form, L was a function of the q and q dot t, and we are defining some new quantity h in the new coordinate system, which is phase space. Okay, new space, phase space, and h is nothing function of q, p, and t, and where p is a function of where p is nothing but del L by del qi dot, where pi is nothing but del L by del qi dot. Okay, so now the question is, how can you relate this age to the Lagrangian? That's the question. And for that, you have to consider the Legendre transformation. So now look for the Legendre transformation. Let's say we have a function that is x, y, f of x, y. And we are going to another function g, which is a function of x, v. Okay? And where v is nothing but del f by del y. Okay, first write down the df. Okay, df is equal to del f by del x times dx plus del f by del y times dy. Okay, and let's say del f by del x equals to u, so u dx plus v dy. Okay, so we are going from the y to the v prime, right? And in the Legendre transformation, this says that we can write down the g in a way g equals to v times y. This is changing to the v, so we have to multiply this v times y minus the previous function. Here can you can also put minus here, you can put plus here. Okay, sometimes here will be positive also, but why I am putting the minus here, you can easily understand after a few lines. If you take the dg here, you'll get what? V dy plus y dv minus df. Df is equal to u dx and v dy. V dy will cancel out, so you will get minus u dx plus y dv. Okay, and I want this. I mean, if the g equals to function of x and v, then you are assuming this del g equals to what? Dg equals to what? Del g by del x into dx plus del g by del v times dv, right? So you are expecting something like this, something dx plus something dv, and you are getting this something dx, something dv. So that is the way. So if you have function f, which is x and y, and we are going to another function g, which is x and v, and v is not a arbitrary parameter. V is a parameter which is connected by write the f in this way, that v is df by dy, then you can write down the g is equal to vy minus f. Okay, so in the similar way, just look for the Lagrangian part. In a similar way, just look for the Lagrangian part. You have a Lagrangian, there is a function of q dot t. In the place of y, there is a q dot. In the place of v, there is a p. V is del F by del y. Here pi is del L by del qi dot. The same way. So you can easily write down the h equals to what? There is a v y. So in the place of v, there is a p and there is a q dot. So as there is a uh, n number of the p and n number of q, so we have to put some summation. There is a qi dot pi minus f. In the place of f, we have a, because there is a f, in place of we have Lagrangian. So our Hamilton will be this. Okay, so we are getting h is equal to summation over qi dot pi minus l. Okay, just now your h is equal to function of qp and t. So what is a dh? Dh is equal to del h by del qi dot plus del h by del pi dot plus del h by del t. That is summation over I, that is summation over I. And from here, do the same thing. What is the dh? Dh is equal to summation over pi dqi dot, no sorry, not qi dot, there will be dpi, right? I'm not doing the dh dt, I'm doing the dh. So dh is equal to this, sorry, and dh is equal to pi dqi dot plus qi dot dpi minus dl, right? And what is a dl? L is a function of what? Q, P and T. Just write down this. Qi dot plus iota qi dot dpi minus summation over del L by del qi dqi plus del L by del qi dot dqi dot plus del L by del T. So I have already said that del by del qi dot is what? Is your pi, and you know from the Lagrangian equation in del L by del qi dot and the time derivative minus del L by del qi equals to 0. So del L by del qi equals to what? Time derivative of this, instead of, I can write down the equal sign. So del L by del qi equals to dt of this, and this is pi. So this is what? Del L by del qi is pi dot. So summation over I pi dqi dot plus summation over I qi dot dpi minus pi dot dqi minus pi dqi dot minus del L by del T, right? And your pi dqi dot here is also, that will be cancelled out, and you eventually get your qi dot dpi minus pi dot dqi minus del L by del T. Okay, this is your dh. This is your dh, sorry, there will be a dt term also, dt term also, dt term also, and here will be also dt term also. Okay, so if you compare this with this, you will get qi dot is equal to del h by del pi, and you will get pi dot is equal to del h by del qi with a negative sign, and you also get del h by del t is equal to minus del L by del T. Okay, so these equations, I mean, this is the qi, that means there is a q1, q2, q3, q3, Q4 is total n number of equation. There is total n number of equation. You are getting two n number of equation. As I have already said that when you are considering the first order differential equation, you have to get, you will get two n number of equations, and these two n number of equation is known as the Hamilton's equation. Hamilton's equation of motion, or sometimes it's canonical equation of motion. Okay, and there is another term that del H by del T equals to minus dH by dt. Now write down this dH by dt equals to what? dH by dt equals to del H by del Qi, as is a function of Q, P and T. So del H by del Qi, your Qi dot plus del H by del Pi dot plus del H by del Ti. There is a summation over I, there is a summation over I. Qi dot is what? Or you can write down this del H by del Qi is what? Minus Pi dot. Okay, and this is Qi dot plus del H by del Pi is what? Qi dot, and this is your Pi dot. So that will cancel out, right? Okay, that means dH by dt is nothing but your del H by del T, and that is nothing but a minus del L by del T. Okay, so that means if your Lagrangian is independent of time, that means Lagrangian explicitly does not contain explicitly time, then your age will not also uh, conclude the time as explicitly. That means the dH or dt will be equals to 0. So let's say that if your dH will be equals to 0, then that will also provide in the information that dH by dt equals to 0. That means age equals to conserved. So you got one concept here, that if your Lagrangian does not contain time explicitly, your Hamiltonian will also not contain time explicitly, and that will lead to the age equals to some constant. That means age equals to conserved. So when your Lagrangian is explicit time, your Hamiltonian is conserved. That is one idea. Okay, that's interesting thing.